This presentation is going to be all about RF data converters, which are the components found on the RFSoC to deal with analog to digital conversion and digital to analog conversion. We'll also look at digital up and down conversion, which is also handled by these RF data converter blocks. To provide an overview of what will be covered in this section, first of all, we'll have a brief review of the overall transmit-receive system that we're trying to build using RFSoC devices. Specifically, we'll look at the multi-rate tasks which are performed in the transmitter and receiver. Following that, we'll consider the RF data converters, or RFDCs, that are present in the RFSoC, including looking at the architecture of these and the programmable options that are present. We'll also have a brief look at the various different device options that are available. Following on from that, we'll shift on to look at digital up and down converter, or DUC and DDC design for RFSoC. There will be some examples to illustrate these, and then finally we'll conclude. Before going further then, just a brief recap on the type of system that we're trying to build with the RFSoC. You can see on the left hand side that we have the transmitter, on the right we have the receiver. We're transmitting I and Q up to some carrier frequency FC, and this can all be achieved in the digital portion of the system. These two phases are then added together, and we transition from digital to analog using the RF-DAC. There's then some relatively modest analog circuitry before reaching the transmit antenna, and then passing across the radio channel to the receiver. In the receiver, likewise, we have a receive antenna, we may have amplifiers and filters, and then the RF-ADC digitizes the signal that's received. We then have another mixer, this time to demodulate, before going through a filtering chain and then passing onwards to further processing stages. One of the things of key interest in this presentation is going to be the multi-rate operations, which are involved in the transmitter and receiver. Looking at this diagram, which gives the transmitter in a little bit more detail, when sending symbols on each of the I and Q phases, there's then a process of pulse shaping, followed by interpolation, prior to the modulation stage. This is necessary because the sampling rate output by the NCO, which generates the sine and cosine carriers, is much higher than the symbol rate of the I and Q symbols. Pulse shaping is also required to constrain the bandwidth of the signal that's ultimately produced and transmitted across the radio channel. The further interpolation stages will involve upsampling and then filtering to remove the images that appear. As we go through this presentation, we'll pay particular attention to this process of what we call digital up conversion, and that includes all of the pulse shaping and interpolation and the modulation stages. To depict these stages in the frequency domain, we can regard these to clarify what's happening with these frequency domain diagrams. After the symbols have been pulse shaped, we end up with a dark green waveform. The spectrum of the signal looks like the dark green example at the top here. This assumes that pulse shaping has interpolated this. This assumes that the pulse shaping filter has interpolated by a factor of 4. There then requires to be some further interpolation to raise the sampling rate much further. And this gives us the light green, and this achieves the light green interpolated signal shown in the center. We also need to modulate the signal with a sine and cosine carrier at a frequency of FC, which you can see in blue. And then finally, as a result of this modulation, we will achieve the pink modulated signal seen at the bottom. Here we have, notice that the signal is centered around FC. Now, looking at the receive side, the signal that's been captured from the radio channel has passed through the RF-ADC and is digitized. The first stage is to demodulate using a mixer which generates a sine and cosine at a frequency of Fc. All of this processing is taking place at the highest sampling rate, Fs, but once the signal has been demodulated, then there's no need to continue processing at that high sampling rate, and we then have a series of decimation filters followed by a matched filter which is matched to the pulse shape used in the transmitter, and then, with some synchronization help of course, we'll end up recovering the I and Q symbols that were originally transmitted. Looking at a frequency domain representation of the receiver's processing, we begin with a received signal which is shown in pink here, corresponding to position A in our previous diagram. This signal has then got to be demodulated, which requires a sine and cosine wave generated from the NCO, which is shown in blue here and labelled with B. At the mixer output we end up with two copies of the received signal, one of them demodulated to baseband as desired, and then a second copy which is at double the frequency, although it may be aliased back down. The baseband copy is the one that we want to retain, and this high frequency copy at twice the carrier frequency, possibly with aliasing, can be removed using filters. After we've performed decimation, then we've removed all of these high frequency components, including the double frequency copy of the signal, and also reduced the sampling rate down so that it's much closer to the symbol rate. However, we're still oversampled by some degree at this point, which aids with synchronization. Now, let's look at a diagram of the RFSoC. Clearly this is quite a high level diagram of the device, and you can see the processing system in the top left, shown in blue, and then most of the device is programmable logic equivalent to an FPGA. The RF data converters are shown in the red highlighted box, and we have two sets. A set of RF-DACs for the transmit side, shown in orange, and a set of RF-ADCs for the receive side, shown in green. The RF-DAC blocks also include digital up converters, or DUCs, which serve to increase the sampling rate through interpolation, as we've discussed on previous slides. Similarly, in the RF-DAC blocks, there are digital down converters, or DDCs, which perform decimation. In each case, the DUC or DDC probably doesn't perform all of the interpolation or decimation that we require, but it does do a lot of the heavy lifting, moving between the very high sampling rates used at the RF interface and the sampling rates that are better supported in the FPGA part of the device. In Gen 1 and Gen 2 RFSoC devices, the maximum interpolation and decimation rates are 8, whereas that goes up to 40 for Gen 3. If you require further interpolation or decimation, that can be achieved by building additional interpolation or decimation filtering stages in the programmable logic. In this table, we can see a summary of the RF-ADCs that are available on Gen 1, Gen 2 and Gen 3 RFSoC devices. First of all, shown in peach, there are the Gen 1 devices, and these contain either 8 or 16 RF-ADCs, with a maximum sampling rate of 4.096 gigasamples a second. The maximum RF input frequency is 4 GHz. In this case, the RF-ADCs have a resolution of 12 bits. There's only one Gen 2 device, and it's quite similar to Gen 1, but it does have some slight differences. The most prominent one being that the maximum RF input frequency is 5 GHz. Then, over on the right hand side in purple, you can see the Gen 3 devices. And there's more variation here in the number of RF-ADCs that are present on each device. You can have between 2 and 16 of them. The maximum rate is up to 5 gigasamples per second here, and the maximum RF input frequency is 6 GHz, so it's higher than either Gen 1 or Gen 2. And additionally, the resolution of the RF-ADCs increases from 12 bits to 14 bits. When operating at these maximum frequencies, the RF-ADCs can work in both the first and second Nyquist zones, and for lower sampling frequencies, they can also operate in higher Nyquist zones as well. The table on the main slide covered most of the available RFSoC parts, but there's also one additional one, which is not shown there, which doesn't actually contain any RF-ADCs or any RF-DACs. Despite this, it's still categorized as an RFSoC because it contains the forward error correction blocks, which also feature as part of RF systems. As you'll notice from the examples that follow, we tend to use a sampling rate of 4 gigasamples per second, and that's because it's an easy number to use. It's slightly lower than the 4.096 gigasamples per second supported by the Gen 1 devices. We're just rounding it so that we can work with easy to use numbers. We've chosen to base the examples on 4 gigasamples a second and Gen 1 devices because it's Gen 1 that features in the RFSoC 2x2 board that this course is based around. Given the 4 gigasamples per second sampling rate that we assume here, then the ADCs in RFSoC can operate in the first Nyquist zone from 0 to 2 GHz. In order to do this successfully, an analog anti-alias filter must be included prior to the RF-ADC. This has the effect of attenuating all other frequencies which would otherwise alias into our bandwidth of interest. The upper frequency spectrum, shown in red, indicates the bandwidth of interest in the analog domain. After the RF-ADC, this signal will be captured and represented in the digital domain. Thinking about different types of radio signals that may be found in this first Nyquist zone, up to 2 GHz. That includes things like GNSS navigation systems, broadcast television, IoT standards such as LoRa and NB-IoT, and also several of the cellular bands. Of course, this is just the tip of the iceberg, and many other systems will also use this band up to 2 GHz. Now, let's look at how the RF-ADC will operate in the second Nyquist zone, where the signal of interest lies between 2 GHz and 4 GHz. In this case, the analog to digital conversion process exploits aliasing. The band between 2 and 4 GHz will be aliased down into the band between 0 and 2. This means that the band between 0 and 2 should be completely empty of other frequencies prior to the analog to digital converter. And for that reason, it's important to include an analog bandpass filter, which will capture the band between 2 and 4 GHz and attenuate all other frequencies prior to the analog to digital conversion stage. These principles would also work for the third Nyquist zone and higher, although with the sampling rate set to 4 gigasamples per second, the third Nyquist zone actually wouldn't sit within the bandwidth of the RF-ADC. It would, however, work if the sampling frequency was set to a lower value. A variety of well-known standards use the 2 to 4 GHz band. Examples include 2.4 GHz Wi-Fi, Bluetooth, Citizens Broadband Radio Service or CBRS in the USA, various different cellular bands, and so on. Most RFSoC devices have either 8 or 16 RF-ADCs. They can either be grouped as dual RF-ADC tiles, where there are 2 RF-ADCs, mixers and decimators, or it can be a quad RF-ADC tile, in which case there's 4 of each component. Taking first of all the example of a dual RF-ADC tile, then we have a shared sampling clock which applies to both of the RF-ADCs in this tile, and then the mixers and decimators have been grouped together to form 2 digital down converters, and it's this unit which we'll go on to discuss in more detail later in the presentation. For the quad RF-ADC tile, then as its name suggests, there are 4 RF-ADCs, each with its own digital down converter. One of the really interesting features about the RF-ADC blocks is that they can do multiband operation. And this means that a single RF-ADC can be used with its output being fed to multiple different digital down converters, each tuned to a different frequency corresponding to the various bands to be captured. The quad RF-ADC tile can support up to 4 bands, and the dual ADC tile can support 2 bands. We're now going to move on to look in more detail at the DDC, starting with the digital IQ mixer. This component has the job of mixing or multiplying the incoming signal with sine and cosine waves. These sine and cosine waves are generated by a numerically controlled oscillator, or NCO, and the frequency of the NCO is one of the programmable parameters of the block. This diagram explains the functionality of the digital IQ mixer. We have a signal which is captured by the RF-ADC, which we assume is a signal of interest centered at the frequency Fc. If sine and cosine waves are then generated at that particular frequency, we end up demodulating the signal to baseband. In other words, a copy is centered at 0 Hz. At the same time, some high frequency terms are generated at 2 Fc. These are not necessary or desired, but they can be filtered out with a low pass filter. The IQ mixer can actually operate in 3 different modes. These are coarse, fine, and bypass modes. As the name suggests, the bypass mode simply means that the IQ mixer is bypassed and we don't use it. The coarse mode allows the incoming signal to be mixed with a very limited set of frequencies, which can be generated with very simple NCOs, therefore saving on power. The fine mode, which is shown in yellow here, allows any arbitrary frequency to be generated. The second part of the DDC to consider is the decimator, and this is a programmable component which can undertake rate change reductions by a factor of 1, which is trivial, in other words it stays the same, 2, 4 or 8 in Gen 1 and Gen 2 RFSoCs. These decimation ratios are achieved using a set of half-band filters, which are labelled FIR0, FIR1 and FIR2, and we've depicted them here in pink, blue and green. Each of these decimate by a factor of 2, and therefore they can be cascaded to achieve ratios of 4 and 8 as well. Effectively, a multiplexer makes a choice between these different decimation ratios, and then passes data out of the RFDC block into the programmable logic section of the device. Half-band filters are used here because they are particularly computationally efficient, as well as having symmetrical filter weights, which cuts down on the number of multipliers required. Every second weight, apart from the central one, has a value of exactly 0, and therefore these computations can also be removed. Looking at the frequency responses of the FIR 2, 1 and 0 filters on the right hand side of this slide, you might notice that they have different responses, and as a result they have different numbers of weights. The design of the different half-band filters in the RF-ADC's digital down converter exploit the fact that at certain stages of down conversion, more relaxed frequency responses can be used. We'll now go on and explain why this is the case. As an example, let's look at decimating by a factor of 4. In this case, we have the FIR1 and FIR2 filters in cascade. FIR1 decimates by a factor of 2, and so does FIR2. The frequency responses of both of these filters can be plotted on a single axis. Both are referenced to the input sampling rate fs. This allows us to clearly see how the responses of the two filters interact. Noting that the green filter FIR2 would only be applied to samples exiting the FIR1 filter, and therefore at half of that sampling rate, then we actually need to plot an image of FIR2 against the FIR1 filter. The blue filter has quite a relaxed frequency response because it only needs to have strong attenuation in the passband region of the green filter. We can now look at the combined response of this cascade of two filters, which is shown in dark turquoise here. Notice that the passband region closely corresponds to that of the green filter. The stopband region is a little less even, and that's a result of the interaction between the blue and green filters. But overall, we've been able to achieve the desired result, which is a filter passing approximately a quarter of the band, and with high attenuation at all other frequencies. A similar approach can be taken if analysing the decimation by 8 configuration, although we'll not look at that explicitly here. Over the next few slides, we're going to look at some examples. Here, the signal of interest resides between 400 and 700 MHz, and our sampling rate is 4 gigasamples per second as before. Therefore, the signal is in Nyquist Zone 1, and we can use a direct RF architecture to capture it. In other words, there's no requirement for any analog demodulation prior to the RF-ADC. Looking at the diagram then, in the analog section there's a receive antenna, an RF amplifier, and crucially an RF low-pass filter to attenuate any signals which would otherwise alias into the bandwidth of interest from 0 to 2 GHz as a result of the sampling process. The RF-ADC operates at a sampling frequency of 4 gigasamples per second. The mixer must be set to generate a sine and cosine wave at a frequency of 550 MHz, because that corresponds to the centre of the band of interest. The decimating filter chain is then set to decimate by an overall factor of 8, which reduces the sampling rate to 500 megasamples per second. And at that point, the IQ samples are passed into the programmable logic section of the RFSoC. Now, let's have a look at the frequency domain representation of the processing that's undertaken in our receiver. In the top diagram here, we have an analog signal, depicted in red and orange. Our signal is between 400 and 700 MHz. And importantly, we said that an analog low-pass filter was required to make sure that any higher frequency components are removed prior to the analog to digital conversion process. To depict the digital signals after sampling, we've changed the colour to blue. As the signal is complex, then it's represented on this positive and negative axis. You can see the positive components between plus 400 to 700 MHz and the negative components between minus 700 and 400 MHz. As our sampling rate is 4 gigasamples per second, this is inside Nyquist Zone 1. What happens next is shifting of one of these copies, either the positive or negative, so that it's situated around 0 Hz, in other words at baseband. Here, we've chosen to shift the positive frequency components to 0, and the reason for that is if you look at the shading of each of these signals, the darker side should be on the right, and that corresponds to the positive frequency components in the second diagram. After shifting to baseband, then the sampling rate can be reduced. There is no reason to continue sampling at the high rate of 4 gigasamples per second. So after decimating by 8, the sampling rate is reduced to 500 megasamples a second, and all of the higher frequency components are removed, leaving the signal that you can see in the bottom diagram here. We'll now briefly look at a simulation in Xilinx, which confirms the different stages depicted on the last slide. Firstly, the box on the far left-hand side represents the received signal. We're not too concerned with how the signal has actually been created here, just the key parameters. You can confirm here that the sampling rate has been set to 4 GHz, the signal bandwidth to 300 MHz, and the carrier frequency to 550 MHz. In other words, the centre of the band between 400 and 700 MHz. We've also chosen to add a spectrum orientation tone, which will help us to confirm which way round our signal spectrum is at different stages. Next, let's run a simulation and view the results. First, we'll take a look at the spectrum of the received signal. Here, we can confirm that the signal extends from approximately 400 to 700 MHz as expected. Notice the spectrum orientation tone, which is a slight spike sticking up towards the right-hand side. The next spectrum scope shows the signal directly after the RF-ADC. At this point, the received signal has passed through an analog low-pass filter, and it has also been digitized at a sampling rate of 4 gigasamples per second. Notice again that the bandwidth of the signal is 300 MHz, centered at 550 MHz, and with the spectrum orientation tone shown on the right-hand side. Next, we'll take a look at the spectrum after demodulation. As we now have two phases, I and Q, the spectrum becomes a complex one. Notice the position of 0 Hz, halfway along the x-axis. After demodulation, we have centered one of the images at 0 Hz as desired, and there's also another one at negative frequencies. Notice that these are mirror images of each other, and therefore the spectrum orientation tones appear at opposite sides. The image which has now been centered at 0 Hz is the one which we want to retain. Now, finally, let's have a look at the spectrum of the signal after it's passed through the decimator. Remember that the decimator performs low-pass filtering, as well as reducing the sampling rate. The sampling rate has now been reduced by a factor of 8 to 500 MHz. In this spectrum scope, we can see the decimated signal with the spectrum orientation tone on the right-hand side as desired. Let's now move on to consider an example where the frequency band to be demodulated is in Nyquist Zone 2. Again, we'll use a direct RF architecture with no analog demodulation required. As we're working in Nyquist Zone 2 this time, a bandpass filter is required in the analog domain prior to the data converter. This means that Nyquist Zone 1 will be largely empty of any other signals. Therefore, at the sampler, then the signal from Nyquist Zone 2 will alias down into Nyquist Zone 1. After that stage, the mixer will then demodulate using an NCO to move a copy of the signal to 0 Hz. Thereafter, the decimator will this time be set to decimate by a factor of 4, and therefore the samples will be passed to the programmable logic at a sampling rate of 1 gigasamples per second. Let's now confirm what's happening in the frequency domain as a result of these different steps. To begin with, we have an analog signal, again depicted in orange and red, which is in Nyquist Zone 2 this time. We have an RF bandpass filter isolating Zone 2, which will therefore attenuate all of the noise present in Zone 1 and in higher frequency bands. Notably, the red, darker shaded side of our signal is at the high end of the frequency band from 3 to 3.5 GHz. As a result of aliasing, then the direction of this signal reverses, and in the first Nyquist zone, in the positive section, our signal is present between 500 MHz and 1 GHz, but the darker shade is now on the lower side of that band. We also have an image in the negative portion of the frequency spectra, and this has the darker shading on the right-hand side. It's therefore the negative frequency band that we choose to move to baseband in this case. As the signal bandwidth is greater than before, this time we choose to decimate by 4 rather than 8, and therefore the final sampling rate here is 1 gigasamples per second, as you can see in the bottom diagram. Of course, there are situations where the frequency band is too high to be captured directly, either in Nyquist Zone 1 or Nyquist Zone 2. In this example, we will consider that an external analog mixing stage is necessary to bring the signal down from its original RF frequency band to an intermediate frequency band that can be digitized by the RFSoC. In this example, we consider a bandwidth of 100 MHz, which is centered at 5.85 GHz. In the analog domain then, after the antenna and RF amplifier, we have an RF bandpass filter which is situated around this 5.85 GHz frequency band. An analog local oscillator with a frequency of 5.55 GHz is used to demodulate from RF to IF. Then there's an IF amplifier followed by an IF low-pass filter, which is cutting off at 2 GHz, matching our Nyquist Zone 1 requirements. The signal is then applied to the RF-ADC and enters the digital domain. Here, the sampling rate is 4 gigasamples per second. The IF mixer then requires to demodulate from the intermediate frequency, which is centered at 300 MHz, down to baseband, and therefore the NCO produces tones at 300 MHz. Following that, the decimating chain can implement a decimation by 8, and the IQ samples are passed to the programmable logic at a sampling rate of 500 megasamples per second. Once again, to confirm the operations in the frequency domain, we begin with our signal centered at 5.85 GHz in the analog domain, and then in the second frequency domain plot we're still in the analog domain, but this time demodulated down to the intermediate frequency. Thereafter, the subsequent steps correspond very closely to the examples we've already looked at. A fourth possibility, using RF-ADCs in a pair to deal with a complex input, is required for situations where the signal bandwidth is too wide even to be accommodated by a 2 GHz wide Nyquist zone. We don't have time to dwell on this example here, but it would allow, for instance, a 3 GHz wide signal centered at 27 GHz to be successfully captured. So far, we've spent a lot of time talking about RF-ADCs. Now it's time to turn our attention to RF-DACs. This table shows the selection of different RFSoC devices across Gen 1, Gen 2 and Gen 3, and their respective numbers of RF-DACs and the resolutions and sampling rates that each of them have. As you can see, Gen 3 provides the highest sampling rates. We are once again going to focus on Gen 1, and notice that the first column for Gen 1 has a total of 8 RF-DACs, with a maximum sampling frequency of 6.554 gigasamples per second. Similar to RF-ADCs, RF-DACs can work in the first and second Nyquist zones, although using a different technique than we've covered so far. The organisation of RF-DACs on the chip is very similar to that for RF-ADCs, although in the case of RF-DACs, there are always quad tiles, with 4 sets of interpolators, IQ mixers and RF-DACs. We don't actually need to spend too much time on the RF-DAC blocks, because they're very similar to the RF-ADCs, just with the opposite set of operations. As you can see in this diagram, IQ signals enter the RF data converters and then pass through a pair of interpolators. This time interpolators are required to raise the sampling rate, but the ratios are the same as for the RF-ADC decimators. Ratios of 1, 2, 4 and 8 are supported, with 1 being a bypass mode. The IQ mixer generates sine and cosine waves with which to modulate these signals, and then they're added together and passed to the RF-DAC block. The sampling rate of the RF-DAC is programmable and can be up to 4.096 gigasamples a second for Gen 1 devices. In the interpolator, a set of 3 identical filters are required as compared to the RF-ADC. So the green, blue and pink filters here have exactly the same responses as we saw earlier. This time, of course, they're interpolating. The order of applying the filters is different, but overall you can see the similarities between this and the decimator that we looked at earlier for the RF-ADC. Over the next couple of slides, we'll look at the operation of the RF-DAC data converter itself, starting with Nyquist Zone 1, which we can think of as a conventional zero-order hold operation. That means that for every sample output from the RF-DAC, the analog waveform that's generated looks like this steppy waveform seen on the left-hand side. This signal would normally then pass through an analog filter which would smooth out the steps. Looking at the frequency response though, of this zero-order hold steppy signal, you can see the shape that would be generated. Here, the majority of energy is concentrated in Nyquist Zone 1, as you can see in the diagram on the right-hand side. You may also notice that there's a drop-off in magnitude across that zone, and that can actually be corrected with an inverse Zynq compensation filter, which is an option in the RF-DAC block. When operating in Nyquist Zone 2, the RF-DAC works in mixed mode, and this means that the signal generated as a result of digital to analog conversion alternates between positive and negative values corresponding to each sample. That's shown in the diagram on the left-hand side. On the right-hand side, you can see the resulting spectrum. And this time, you might notice that the highest amount of energy is concentrated in Nyquist Zone 2. It's slightly down in terms of overall energy compared to our Nyquist Zone 1 normal mode example, but there is still a significant amount of energy in that zone, and moreover it's relatively flat across that zone as well. Although it's less necessary to apply a correction in Zone 2, Gen 3 devices have introduced an additional option for inverse Zynq compensation in Nyquist Zone 2 as well as Nyquist Zone 1. This completes our overview of the RF-DAC block. Perhaps the most interesting part of the RF-DAC block is the data converter itself, because it's got this option of mix mode to generate signals in Nyquist Zone 2. Finally, to conclude this presentation then, we've given a brief overview of the RF data converters within RFSoC devices, in particular focusing on the operation of RF-ADCs and RF-DACs. We've seen that RF-ADCs exploit aliasing and can operate in the first and second Nyquist zones. RF-DACs, on the other hand, operate in a very different way They use a special mix mode to generate signals in Nyquist Zone 2. We've also looked at the functionality of the digital up converters and digital down converters that are present in the RF-ADC and RF-DAC blocks respectively. We looked at several different examples of radio signals in different bands and how these could be supported by the RF-ADC configuration. Notably, we were able to observe that several different popular radio standards could be supported in either the first or second Nyquist zones, given an RF sampling rate of 4 gigasamples a second. And therefore we can conclude that there is lots of potential to use the RFSoC for many different applications.